Aphids are small insects capable of reproducing asexually. That is, an unmated female can essentially give rise to daughters that are perfect clones of herself. An individual adult aphid like this one may only weigh a milligram. But these very small insects can reproduce rapidly. If she's got enough food and space and there aren't any predators, one female aphid can give rise to 8 offspring in about 5.5 days. That's impressive in its own right, but what's really impressive is what happens if you let this process keep going. If every one of these offspring here reproduces, generating 8 more aphids in 5.5 days, and each one of those 8 offspring generates 8 new offspring in 5.5 days, and so on, then in 6 months, the pile of aphids that you would end up with would weigh more than the planet Earth. It would actually take 7 or 8 months for it to outweigh the sun and all of the planets in our solar system. And in less than a year, that heap of aphids would weigh more than everything in the known universe. This is what is known as exponential growth, and it is staggeringly powerful. If you know something about economics, exponential growth is a little bit like compound interest. If you invest some money in some account, and when you earn interest on it, you just plow that interest back into that account, you start earning interest on your interest. And then if you plow that interest back into the account, you're earning interest on your interest on your interest, and so on. The more money you earn, the faster you accumulate interest, and the faster you accumulate interest, the more money you've got in that account. The growth of the amount of money in the account just keeps on accelerating, and it can become very large quite quickly. We've been talking, or before the quiz rather, we were talking about the different levels that ecologists might study ecology on. One of them was the population level. One of the most important things that ecologists study on the population level is just population size. How many individuals are there in this group of, say, deer or fish or plants that are all in some relatively well-defined area? When they're thinking about population size, ecologists are generally concerned with one of two things. One is how many individuals are there. That's a pretty basic thing that you might want to know. But another thing that you might want to know is this population growing or shrinking? And there are a few reasons that you might be concerned about this. One is that, for example, there are some species that are pests. This is the emerald ash borer. It's very harmful to ash trees. And one thing that ecologists are very concerned about is how quickly are its numbers increasing, and therefore how quickly is it spreading and killing ash trees in the United States. Or, say you might be interested in a species that has some kind of economic value. So tuna, for example, are very valuable as food fish, and we're quite concerned about how many of them there are out in the oceans. And particularly because many fisheries are on somewhat shaky ground, we'd be worried if we realized that the population of tuna worldwide was shrinking, for example. So what kind of tools can ecologists use to study these things? Well, let's take a look at some approach that we might be able to use to think about whether a population is growing or shrinking. Suppose you've got 2 fish. You've got a male fish and you've got a female fish that love each other very much, and they get together and they have little baby fish. First, we're going to take a look at exactly what happens mathematically. And yes, we are going to go through some math and figure out the exact calculations, but then I'm going to show you an easier way of approaching at least simple equations that should be of great value to those of you who are math phobic, because often you don't need to do the exact numbers. You just have to have a gut feeling for the way that an equation is going to behave. Let's take a look at the exact stuff first, though. If you've got 2 fish, they might have together some number of offspring that make it to adulthood. That number could be as low as 0, and there's really no upper bound to how high that number could be, but this graph we're only going on up to 4. Okay, if on average, a pair of tuna who love each other very much have 3 offspring, making it to maturity, then you've got 3 offspring entering the population for every 2 parents that ultimately will leave the population. That is, they'll die of old age. If the average generation time of a tuna is about 8 years, which it happens to be, I looked it up on Google, then the rate at which this couple of fish is changing the population size is 0.125 fish per year. That is, this couple of fish is increasing the fish population at this rate. Why don't you notice a couple of other things here? This number, of course, dramatically depends upon how many offspring these fish are actually able to have that make it to maturity. If they have 2 offspring, they're exactly replacing themselves. And so they're actually adding no fish per year to the population. If less than 2 of their offspring make it to maturity, then in fact, there's going to be a net negative effect on the population size. For each pair of fish you have in the population, you're going to be adding 1 offspring and taking away 2 parents. So the effect of having these 2 fish in the population will actually be a negative. It'll be minus 0.125 fish per year. Okay, why are these numbers useful? Well, there are a couple of things that you can do with them. One of the most interesting is this. Suppose that you've got 1,000 fish in a population. That makes 500 pairs, and on average they're going to be like this one. If each pair is actually having 3 offspring making to maturity, that's plus 0.125 fish for each pair per year. 0.125 times 500 is equal to plus 62.5 fish per year. That is, the whole population is going to be adding this many fish per year. What we're doing here is we're building what's called a mathematical model. It's a very simple one, but it's very easy, once you've got these numbers, to be able to calculate what's going to happen to a population in the future. In this case, we've got a rate of population growth, that plus 62 fish per year. We've got the rate of increase down here at the per capita or per fish level. That's 0.125 new fish per pair, per mating pair. And then we've got the population size, which in this case is 500 pairs. We can write this in the form of a simple equation. And this is how ecologists usually write this equation here. The rate of population growth is written as delta n, the change in the population size over the change in time. The rate of increase that's described in your book is little r. And then there's n, the population size. This is what's called the exponential growth equation, and it's the simplest possible model of population growth. This is the equation that I use to calculate how long it would take for a single aphid to create so many offspring that they outweighed the entire planet Earth. So that's how you deal with it if you kind of liked doing math, or at least tolerated doing math. For most purposes, though, including practically all of this class, you don't have to think about it in terms of the exact numbers. It's good enough for you to have a kind of a gut feeling for the way that this equation is behaving. And let me show you what I mean by that. For every pair of fish in a population, they're going to have some number of offspring. Okay? And really what's important here is, are the fish replacing themselves or not? Yes or no? Okay? If there's some number up here, the population is growing. If they're producing exactly 2 offspring on average, the population stays the same size. And if it's less than 2, the population is shrinking. So all you really have to do is kind of look at this number. Okay, there are 2 fish. I know if they produce 2 offspring, they're exactly replacing themselves. Any more than that, the population grows. Any less than that, the population shrinks. There's no real math involved here. It's just kind of recognizing whether a population is growing or not based on how many offspring each mating pair is leaving behind. In the same way, you can look at this equation in a sort of gut feeling kind of way. Okay, any equation is really just a balance. Okay, you've got the equal sign here in the middle of the fulcrum. And over here on this side, you've got this term. What does that mean? It means how fast is this population growing? Okay, what have you got on the other side? You've got basically a big square. It's R wide and it's in high. What does that mean? Well, it means that if you increase the height of this block over here, this over here has to increase in order to keep this teeter-totter balanced. In the same way, if you increase R, this has to increase in order to keep the teeter-totter balanced. In other words, as the number of individuals in the population increases, the speed at which the population grows becomes faster. As R, this rate of natural increase, goes up, the rate at which the population grows is faster. And that's good enough. If you understand those points, just looking at this equation, that's good enough for most purposes. So what I'd like you to do during this course is we won't be playing with math too much, but I'd like you to develop the ability to look at an equation like this and see, okay, I recognize if I just kind of look at it and think about it and maybe plug in a few really simple numbers like say 0, I'm going to look at it and see some basic facts about this equation just from a gut approach. I'd be able to look at this and say, oh, okay, if R is some positive number, that is, if each pair of fish is more than replacing itself, if it's having more than 2 offspring on average, then the population's growing. If it's less than 0, then the population is shrinking. If R is exactly 0, then the population stays the same size. Similarly, you should be able to look at this equation and realize, oh, you know, the larger R gets, the bigger this number over here is going to be. What that means is that as R gets larger, the population is going to grow faster. And as the population gets bigger, it's also going to grow faster. Those are the sort of things that I want you to be able to look at an equation like this and see right away without having to do any real math at all.